All right, we're going to be taking a look at kind of two concepts that are very closely related. Either we're doing the area under a curve or the area between two curves. Now, how this works is that let's say we have, in this case, two different curves, and let's call them y1 and y2. Okay? And these are both continuous on a certain interval, which means there's no breaks, right? And we want to try to find the area between these curves. Let's say let me draw another example here. Let's say we have, here's some parabola that's going to be opening up. And let's say I had another parabola that was kind of coming up like this, right? Oh, and let's say I wanted to find the area from a value from here to here, right? So I'll kind of add some dotted lines. So that'd be all this space inside of here, right? The problem with that is that's not in a regular shape, right? This is not like a rectangle. This is not a triangle. You don't have a formula to just calculate that value very easily, right? So doing like simple geometric properties isn't going to work. But we need another way, and that other way is going to be using integration. Now, integration is like a fundamental concept when we're doing calculus, and what it allows us to do is to divide that interval into very small, very tiny rectangles. And if we take the sum of all of these rectangles, right, and we add up all those areas, we will get the total area under the curve, which you can kind of see what I've done here, right? If I just make an infinite number of very tiny rectangles and I fill in that space, I can add all those rectangles together to get the area, right? And basically that property, that is what a definite integral is doing. Now, if you want to look up a little bit more about where this comes from, you can look up something called a Riemann sum, and that you can do a little bit extra research on like why this works or where this is coming from. But let's just kind of look at the applications. In the process of an integral, right, we take the bigger number and that goes on the top. Right, so b is larger than a. And how we read this is we take the integral from b to a of y1 minus y2, the larger function minus the smaller function. Okay. And once we integrate that, we can sub in our values for b and a into x. That will give us an actual numerical answer for the area of the space. Let's see how that works with two functions like this. So we have y equals x plus 2. And we have y equals x squared plus x minus 2. And we want to try to find the area between the two curves. So the first thing we're going to do is let's graph this function, right, and find the points of intersection. Now, just for time, we know how to do this. We could graph a straight line and a parabola. We can find where they intersect. I have it graphed already here. So here are my two functions. My parabola is in red, linear functions in blue. And I know that I could figure out the area now between these 2 points is going to be all of this space right in here. In terms of my integral, I need to know, well, what are the x values that I need to be kind of going on my bounds? And here, I notice that the smaller x value is negative 2. That's where I need to start the integral. And the other point of intersection is at positive 2, right? And when I integrate these two functions, right, which run negative 2 and positive 2, they will give me the area in between those two curves. All right, so let's kind of go back here to the other page and let's kind of apply everything we just talked about over here. So we've now graphed the curve. We found the points of intersection, which is negative 2, 0. Right, that was point number 1. And 2, 4 was the other one. Now we're going to solve this problem without a GDC. Obviously, our GDCs can do this very quickly. But our area, again, if I write this in terms of the definition of the integral, is the integral from 2 to negative 2 of y1 minus y2. How do I know which one is which? Right? If I go back to the curve, whatever is on the top, the function above that is greater, is y1. So this is going to be our linear function, is y1. And our curve, because it's beneath the linear function, this will be y2. So our integral would be x plus 2 minus x squared plus x minus 2 dx. Now I can simplify that integral. I'm just going to zoom in here because this is going to be a little bit big. Right? If I go from 2 to negative 2, this would be negative x squared. X minus positive x, those would cancel out. 2 minus negative 2 would then be positive 4. dx. All right, let's do the actual integral now. When we take an integral that has numbers here, the definite integral, right? You're probably gonna notice this from past videos. I always draw like a rectangle here. And now let's take the integral. So this would be negative. And the integral of something squared would be 1 over 3 x cubed plus 4x. And then I write the numbers here, 2 to negative 2. Sometimes you'll see textbooks do this with like a straight line, but I always like using brackets because it's familiar. Now, how we sub in these values is I do the function when it equals 2 minus the function when it equals negative 2. So how that works would be negative 1/3 of 2 cubed plus 4 times 2. Right, that's the first part, minus the same function, a negative 1 over 3. So I have negative 2 cubed plus 4 times negative 2. All right, let's simplify this. This would be negative 8 over 3 plus 8 minus, this would be positive 8 over 3 minus 8. Now, if we're trying to kind of like now solve this question, we have negative 8 over 3 here, minus 8 over 3. And we have 8 minus negative 8. So this would be 16 minus 16 over 3. And if we wanted to simplify this even further, we could write this all as something over 3. So 48 over 3 minus 16 over 3, which would give us the final answer, which would be 32 over 3. That is the area between these two curves. Okay. Now, if we want to do this on our GDC, it would be the exact same process. We'll show you how to do this in class. You go to our GDC, to the integral function, put in our bounds, write in our function, and we would have our answer right off the bat. All right, let's do another example here. So we have now a function that is not so nice. You're probably looking at this and going, would I ever have to graph this by hand? No. This would be something that we would always be doing with our GDC. All right. So we have here, graph the region bounded by the curves, find the points of intersection, write down an expression that gives the area of the region. Again, this part here we'll go over in class. I just want to go over the last part. When we want to do the integral on our GDC, all we kind of need to know when we plug this in is what function is higher and what function is lower, right? Now, when I go into Desmos, let's say I have this here, and I'm plugging this in, right, or on your GDC, you're just going to try to figure out which one is the top function, that's your y1 function, and which one is your bottom function, that's your y2 function. I want to do this whole example in class, right? So you can try it on your own, but we will take this up in class with GDCs just so you understand how this works. But remember, the only time you're ever going to need to like do this graphing process by hand is if you have functions like this that we're familiar with. Anything involving lawns or EDX that are kind of gross functions, this is guaranteed going to be on your calculator paper. Okay, so in general, for this lesson, all we really need to take away is that the area under or between two curves, right, all we need is two x values, which are going to be our bounds that we plug in, and it's always the top function minus the bottom function. You plug in the bigger x value first and the smaller x value second. Hey, we'll hammer this out in class. I hope that made sense. If you have any questions, please ask